compare those sums of ranks. Here's an example. There was a study done on marathon runners. Ooh, it's a cross-sectional study. Marathon runners tend to spend a lot of time in the sun, so they develop a lot of skin lesions from sun exposure. They develop something called nevi, which can be precursors to melanoma, so they're worrisome. And researchers wanted to know whether or not more sun exposure would increase your nevi. That's expected. They also were curious to know whether or not if you're a marathon runner who trains more intensely, who trains faster, who trains harder, for the same amount of sun exposure, if you are more likely to develop nevi. The thought being that somehow that intense training is maybe going to wear down your immunity, is going to make you more at more risk for skin cancer. And so here's the results looking just at training velocity. They grouped people according to their training velocity, a slow group, a medium group, and a fast group. That last group on the right is the fastest group. Then they counted up their nevi. Here are the box plots for the nevi counts. Our outcome variable here is nevi counts. It's clearly not normally distributed, right? We have very much right skewed data. We would not expect nevi counts to be normally distributed. So how would we test whether or not those three groups are different? Well, clearly, since we have very skewed data here, we're not going to want to apply ANOVA. Our sample size is reasonably small here. It's 150 marathon runners, so it's roughly something like 50 in each group. That's small enough with such skewed data that we're going to not want to rely on ANOVA. We're going to want to use a non-parametric test. So how did I get to that? We want the Kruskal-Wallis test. I want to know whether the nevi counts differ according to training velocity group, slow, medium, or fast. My outcome variable is nevi counts. It is a continuous variable. It's actually a discrete variable, but you know, it's a numerical variable. Is it normally distributed? No, it's definitely not normally distributed, and we are also dealing with a relatively small sample size. The observations are not correlated. I have 3 independent groups. I have groups being compared. It's not 2 groups being compared, it's 3 groups being compared, so that leads me to want to do the non-parametric ANOVA, which is called the Kruskal-Wallis test. When that non-parametric ANOVA is run, again, it's basically the same logistics as the Wilcoxon rank sum test, so I'm not going to go into it in any great detail. It involves ranking and adding up the ranks within those groups. It turns out that there is a significant difference in nevi count across the 3 groups. Now remember, all that ANOVA tells you, it's a global test, so it tells you that at least one of those groups differs. It doesn't tell you which groups differ. The authors went on further. They wanted to know exactly where those differences lay, however. So they went on further and applied the Wilcoxon rank sum test to do the pairwise comparisons here. But they adjusted for multiple comparisons. They adjusted for the fact that they were then doing 3 tests. And it turns out that they could show that the lowest velocity group, the slowest group, differed significantly from the fastest group in terms of nevi counts.